Hello, good afternoon. My name is Stuart Marks. I work at Oracle on the JDK, and I'm here today with my colleague Brian Getz, and we're going to be talking about API design and how Java 8 language features and APIs have impacted the nature of API design. So I'm going to start off a little bit talking about what is an API, at least, or not in fully general terms, but what I'm going to talk about when I talk about an API, and the interaction between API design and language design. And then, as you know, there are many, many features added to Java 8, and these all have a big impact on API design. So I'm going to run through a series of examples of how API design in Java is impacted by these Java 8 features. So these examples are mostly all drawn from the JDK, but they can certainly be applied to your own programs. So during the talk, Brian's sitting up front here, and there you wave just there. And so he will be monitoring Twitter for questions. And so if you have questions, I'd like you to tweet questions using this hashtag, DV14API. All right, just a quick recap of what I mean when I talk about an API. I think of it as an interface between two different pieces of software. And in general, it could be a network protocol or file format or something like that. But really, for this talk, this is about Java, and this is going to be about the things that you can express between software layers in Java, such as packages, classes, fields, methods, annotations, and so forth. Now, API stands for Application Programming Interface, and that's a bit of a misnomer because it's not always about applications. I think that was its original sense, is between an application and the system. But really, most software today has many, many, many layers, and so APIs exist between all of those layers. So during this talk, we'll be talking about the two sides of an API, the client side, and this is not a network thing, this is just the client or the user or consumer of the API, and the library who has defined the API and has provided an implementation of the API. Now, APIs, there's lots of layering in software, but they're also units. We're all object-oriented programmers here, so they're units of programs called classes, and classes themselves have an API, and there are lots of classes within each layer, and those are like APIs as well. So really, APIs are everywhere, and to program is to design APIs. So just a couple quick diagrams here about what I mean. So if we have two software layers, the interface between them I'm calling an API. We have the client is consuming the API, and the library implements it. But this exists in most layered software in a bunch of different places. So if you have several layers in the software, there are APIs at every level. And within one layer of APIs, you might have a bunch of classes that talk to each other. And in a sense, they talk to each other through APIs. All right, so API is about how information flows between these different chunks of software. And the big point about languages is, with programming languages, how that information is represented. And if you change the programming language, then you potentially create new ways of representing this kind of information. And so your API designs ought to take that into account for better expressivity or better explanation of semantics. So clearly, programming language design drives API design. But it actually works in reverse as well, because when you're writing an API, sometimes you say, gee, I want my library or I want my class to do this, but I can't express that in the programming language I currently have. So what ideally should happen, and I think has happened in the past, is this kind of desire or requirement gets pushed back into language design, and the language designers say, oh yeah, so what we need to do is add this feature to the language so that programmers can write APIs that do something that's closer to what they want to do. So we see this feedback loop between language design and API design. All right, let me talk quickly about some Java history here. I'm not going to go through the entire history, of course, but in 1.0, some of you might recall the language was much, much simpler to the way it is today. There were classes, interfaces, methods and fields, and inheritance and so forth. And so it was basic object-oriented programming stuff. And in Java 5, perhaps one of the largest changes to the programming language, generics were added. And notice, generics are sometimes called parameterized types. And so that's a very important concept, is parameterization. So that's a big change to the programming language. Another change that was introduced was the annotations feature. And so that's not going to impact API design directly, but what I want to do is use that as an example of how the annotations API uses generics and how it would be different if there weren't any generics. And so actually at the bottom of the slide is one generic method from the annotations API. Basically takes a class that represents an annotation type and gets an annotation that is a member of that type. And it returns it. So it returns it, you pass in an annotation class and it returns an annotation. Now, if you look at the hypothetical non-generic API, so essentially that would be like the erased version. So if there are no generics, then you would just pass in a class. Well, what are the requirements on that class? Can it be any class or can it be an annotation class? And so you can see that something's missing from that compared to the generic version of that. So in the generified API, it's clear that the class that you pass in as a parameter must be a class that represents an annotation type and not some other type in the system. And this is expressed in the API, and the compiler will check this for you. Whereas with the non-generic version, that checking isn't done at compile time, and you might get an error at runtime, or you might get the wrong result, and you have to do some debugging to figure out why that is. So here's a case where generics were added to the language, and it improved the power and expressiveness of this particular API. Okay, now let's turn to Java 8. And so there's, as you all know, there are many, many features added to Java 8. The biggest one, of course, is Lambda. So I'm going to be spending a lot of time talking about how Lambda, the introduction of Lambda has changed APIs in Java 8. A few other things as well. We've augmented interfaces, and so interfaces can now have default methods and static methods. In addition, there's a whole family of new APIs that have been added to Java 8, and those APIs in turn can be used in other APIs and new APIs, and so those too change the way you will write APIs in Java 8. So there's a big impact of all of these on your API design. All right, so let's dive into the Lambda stuff here. All right, so the big point about using Lambda in an API is that it allows you to pass behavior through an API, not just values. So before Lambda, you could call a method, you could pass in objects, primitives, and so forth, mainly values. With Lambda, you can pass in a bit of behavior. And this is a very, very powerful concept, and I have some extended examples that illustrate that. A variation of this is called functions as data. And so this is the whole, again, it's a different way of expressing the whole point of Lambdas. You can express functions as data, you can store them in data structures, pass them as parameters, and return functions as return values from other functions. So this is a huge tool in our API design toolbox. Now, it's not really strictly new to Java because you could always do this with anonymous inner classes. But anonymous inner classes had so much other stuff going on with them. Lots of boilerplate, but also the necessity to create a new class and then create an instance of that class and do overriding and stuff. So while it was possible, it was really a very roundabout way to use anonymous inner classes just to express a little bit of behavior. All right, so let's look at this. So prior to Java 8, the ThreadLocal method was introduced, and if you have the ThreadLocal class. Basically, it's a class that encapsulates a value that is local to any given thread. And what you often want to do with ThreadLocals is to lazy initialize the ThreadLocal. So you don't want to create it up front. What you want to do is you want to have the value initialized just immediately prior to the first use of that value. So the way to do that in the old ThreadLocal API was to instantiate an anonymous inner class, override the initial value method, and then use that. Okay, so then when get was called for the first time, the initial value method would get called, and that would compute compute whatever threat. In this case, it would be the next, some ID value you might want to compute here. But the point is that this is not called until the first time somebody uses the ThreadLocal. All right, how do we do this in Java 8? It's much simpler. You have a static factory that takes a lambda. ThreadLocal.withInitial, we say, okay, just pass in this little bit of behavior that gets called at the first get. So you can tell there's no need for subclassing or overriding or anything like that. So let's put both of those pieces of code up on the screen at the same time. So the top one is the old anonymous inner class bit, and the bottom one is the new API using lambdas. And so the obvious thing, of course, is that the old code is much, much, much more verbose. So there's less typing to do with the new APIs. Okay, so that's nice. But really, the old code has a lot of concepts going on, right? So all that verbosity is a symptom of the concepts that are happening there. We are creating an anonymous class. And so if you've ever tried to explain to a beginning Java programmer what an anonymous class is, right, you know that there's a bunch of concepts there that you have to think about. All right, and then you have to override the right method. It's no use to create an anonymous subclass unless you're doing something interesting with it, like overriding a method. And then only once you've overridden that method, well, you have to instantiate an instance of it. And then once you've overridden the method, then in the middle of that, in the middle of all this extra goop about subclassing and anonymous classes and so forth, you put your little bit of behavior. So all those concepts create all the syntactic noise because it's necessary for that syntactic noise to be there to express all of those concepts. So with the Lambda stuff, we just say, here's this bit of behavior, pass it in, and then the library executes it at the first get. And it's all just right there. And there are many fewer concepts in addition to the syntax being much more concise. All right, so really there's a pattern here, which is a joke if you'll see where I'm going. Subclassing gets used a lot in Java in order to provide behaviors to things. And in a sense, subclassing is great for specialization and so forth, but there's a different use for subclassing that commonly gets used, which is to parameterize or provide behavior from outside. And we've gotten used to this because in 1997, the word in Java was everything is an object, and objects are instances of classes. And so the way you express behavior is by creating a new class. And so it's 2014 now, so perhaps it's long past time to unlearn this. So the pattern, so to speak, here is if you look at the 1990s books on design patterns, there's a whole family of behavioral patterns. And if you look at these, they're basically saying, okay, create this abstract class here and subclass it and provide this bit of behavior here. There are a variety of ways to put this together. But these are all just variations on saying, inject this behavior in or parameterize this behavior in somewhere. So now that we have Lambda, you can just write an ordinary method that accepts this bit of behavior and calls it at the right time or does the right thing with it. And the patterns are all sort of still there, and you can see them if you look carefully, but they're mostly invisible now because all you have is one method that takes a bit of behavior instead of all this extra business about subclassing and overriding. All right, let's talk about another example here, which is kind of an API case history, converting a collection into an array. So a bit of background here that you really have to understand well is in Java, arrays have two characteristics. They have a length and they have an element type. And that they are both specified at the time the array instance is created and they cannot be changed. So if you have a collection and you have a client that's using that collection for something, the client knows what kind of array, what kind of element type that array should have. So the collection has a bunch of elements in it, and we want to move them into an array. So where does that array come from? Or where do these pieces, array characteristics, come from? The client knows the element type that it wants that array to have, but the library, the collection itself, knows how many there are. So these two pieces of information exist on opposite sides of the API divide. So let's rewind all the way back to JDK 1.0 and the vector class. And so this is the way to do this using vector, which is copy into, and it takes an array as the parameter. Now, there's some weird things about this. So first is the library is not creating the array here. It relies on the caller to create the array. So the caller creates the array using the desired element type. Okay, that's fine. But the library, or excuse me, the client has to get the length of the element right. Excuse me, the client has to get the length of the array right. If the client creates the array that's too short, then the library will throw an exception. And so that's not very friendly. So the typical way to do this is to say, okay, well, we just ask the vector what its size is, then create the array using that size, and then pass that array in. But you might see that there's a race condition here, because the vector can change size between the call to size and the call to copy into. So really, in the bad old days of JDK 1.0, the solution was to lock the vector around this call, or to put this inside of a synchronized block. But really, this is pretty cumbersome because it relies on the client to have to know to do this. So I didn't write out the code, but you have to do a synchronized block, and you have to get the size and stuff. So this is not a very good abstraction for turn a collection into an array. All right, in JDK 1.2, the collections framework was introduced, and new APIs were introduced to try to address this problem. So there are two methods on the collection interface. There's one called toArray with no arguments. And so that puts the responsibility for creating the array onto the library side. So the library knows how long to create the array. And so we're not going to get any exceptions out of this if the array is too short, because presumably the library is implemented correctly. But the library doesn't know what element type to use in creating the array. And so it's always going to return an array whose element type is object. So that's the problem with this first one. So the second one is, it's this variation on the old copy into, where the client can allocate the array and pass it in, and elements are copied into it if it's long enough. But if it's too short, then the library says, oh, it's too short, so instead of throwing an exception, I'll be nice and create an array of the right size before filling it in. And there's this little bit here where if the library does that, it creates the array using the same element type as the array that the client passed in. And so if the somewhat idiomatic usage for creating converting a collection to an array of a specific type is to pass in an array of the right type of length 0. And so that way the collection is always going to create, well, presumably if the collection is non-empty, it's always going to create an array of exactly the right type and exactly the right length, and then return that. So this is kind of a weird API because there's a lot going on there. And so it's one of those things too, it's very subtle. You have to read if you ever read the Java doc for this, you have to read it several times to figure out what's going on and why. So in terms of an abstraction, there's this weirdness going on about getting the length and the element type onto the right side of the API in order for the array to be created successfully. All right, in Java 8, we faced a similar issue with turning a stream into an array, and we took a different approach. We have Lambda now. We can pass in a bit of behavior, and in this case, the bit of behavior we want in is create an array of a given with the right type of a given length. Now, the client side knows what type to element type to create the array with, but it doesn't necessarily know the length. So just make that a parameter to the bit of behavior that gets passed in. So in fact, the new API for stream.toArray, you pass in an int function. And so here's some examples of this, which is I have some stream of strings and I want to turn that into an array. So I pass in a lambda that says create a string array of length n. So we pass in a bit of behavior, boom, exactly the right thing happens, easy to understand, easy to implement, and efficient. And in fact, there's a variation here. The second line at the bottom is a variation using the constructor reference to the string array constructor. A little bit more concise than writing out a lambda. Now, we haven't yet gone back to the collection interface to add a to array there. We have an enhancement request to do that. So that seems like something that's likely to get in. But you can see the differences in the API styles. So if we go all the way back to 1.0, there's this weird thing with vector.copy into the collections framework. You can see that there's this kind of wrestling match over well, create the array of the right length but the wrong type, or use this little bit of an API hack about copying the element type of the array, and so forth. So finally, now that we have Lambda, we were able to solve this 18-year-old API design problem in Java. And of course, that couldn't happen until the Lambda feature was added to the programming language. All right, I have yet another example of this going on, which is iteration. And so what I've done here is I've written out the iteration longhand. Most of you probably use the for each loop, or officially it's called the enhanced for loop. But that's just syntactic sugar for creating an iterator and then stepping through it, calling hasNext and next in succession. So it's like, well, okay, what's the big deal with this? So iteration is actually pretty complicated. So how many of you have written iterator implementations? Can you raise your hand? I see lots of people. Looks like more than half the people. Okay, now keep your hands up. Those of you who've keep your hands up. How many of you enjoyed that experience? Okay, all the hands go down. All right, yeah. So, and why is that? Well, it turns out that writing a correct iterator is actually a lot more complicated than you think. So, it has these hasNext and next methods, and usually they're called they're called in lockstep. hasNext, then next, hasNext, then next. But, they don't have to be. And so how many of you remember to write unit tests to cover the case where the client calls next twice in a row? Okay, very few hands go up. Good for you, right? So what you have to do in your iterator is keep some state, and that state has to communicate between hasNext and next. And those of you who have the experience of this, it's sort of, okay, hasNext has to set a bit somewhere and keep a cache, and next uses it and unsets the bit. Oh, but if it doesn't, then the next might have to, if the cache is empty, then it has to either load the state immediately or throw no such element exception. So it's actually really complicated. In addition, once you've extracted that state into the iterator refers to something in an underlying collection. And so you have to constantly go back and check that collection to make sure that it hasn't changed, right? So if the collection had elements removed from it, you're going to accidentally run off the end. Suppose you call hasNext, you look at it, and you return true. So you know the guy's going to call next. Meanwhile, the collection got shorter. So you call next and get an index out of bounds exception. So you have to check for that and potentially do something like call concurrent modification exception if that happened. So there's a lot going on in iteration. And so why is iteration so complicated? Well, the API needs to return not only the next element, but it also needs to return a bit of meta information, which is, are there any elements left? So you might think, well, gee, maybe we should just have just one next method that returns null if there's nothing there. Oh, but you can actually put a null into a collection, so that doesn't work. Well, how about returning an optional? Well, that's new in A, so that didn't exist way back then. How about throwing an exception if you reach the, well, that's really inconvenient. So that's probably why we ended up with two methods in iterator, but since there are two methods, they have to deal with state between them and state with the and you always still have to deal with state, reconciling state with the underlying collection. All right, so the upshot of this is, gee, how complicated could iteration be? It's actually pretty complicated, and the most common thing is, I want to do something for every element, and there's a lot of complicated concepts going on here just to say, do something for every element. All right, you know where this is going. We have iterable.forEach in Java 8, and you just pass in a lambda. And the semantics of this is, do this for each element. And the library just takes care of it. It just does it. And that's it. So it's a really simple API, no separate objects, none of this reconciliation stuff, none of this error checking for concurrent modification exception, because it's all handled in the library. And in fact, it's faster too, because you don't have to separate some state into a separate object. There's one method call in general per element access instead of two. There is some additional considerations the implementation can take if it's a concurrent collection. All kinds of good stuff happen because you can pass in this little bit of behavior and the library can handle it in the best way it knows how, instead of having to have this complicated interaction between an iterator and the underlying collection. All right, one more example of parameterizing behavior with Lambda. So let's look at this code for a while and just kind of read it on the screen and see if you can figure out what it does. I sort of say here, but then you read the code and it's like, what is this doing again? So the case here is if you want to have, in general, a map has has key value pairs, but sometimes you want to have multiple values for the same key. So the typical way to do that is to have a value not be the value itself, but a list of values. So when you do this, there's a special case that happens the first time you add a key, which is you have to create the list first and then add it to it. But if the list is already there, you just go in and add it. And that's what this does. And you've probably, if you do something like this, you have to write this code over and over. It's error prone. Usually, if you're like me, you go, oh, I know I did this before. I could think, oh, that's right, I'll just copy the code from over here. And then, of course, you forgot the special case that code did, and then you got to write your unit test for this and stuff over and over and over again. So this is a classic case for having a library that does something like this. But there really weren't any good ways to express this sort of thing prior to Java 8. So once again, we can use lambdas to pass in this bit of behavior. So here, map has a whole family of new default methods, which I strongly encourage you to go look at. They're very, very useful. But this is just one example of them, which is the new compute-if-absent method. In fact, I believe this was introduced on concurrent hash map first, because it's necessary in order for changes like this to be made atomically. But now these have been promoted to be default methods for all maps. Very, very convenient. And so you can see these two lines of code on here in the middle of the slide. Basically, all we do is we say, if the key is absent, then create that array list. We have a little lambda that says, create that array list. And then compute if absent is carefully structured so that it returns the value that either was there already or had just been computed. So you just go in and add the value to it. So it's really simple to use this idiom now once we have compute if absent. So there's another thing here too, if you just going to go back briefly here. If you look at this pile of code, it's a little too long to be idiomatic for, oh yes, it's a map with multiple values. Although, if you do this enough, you might get to recognize it. But the way we understand and remember semantics is by giving them names. And so map.computeIfAbsent is it doesn't say multiple values, but computeIfAbsent says, aha, this is exactly what it's doing. Whereas the other one had all this conditional logic and stuff that you'd have to understand and interpret before you realized, oh, this is doing a computation if the key is absent. All right, so I just went through several examples of this idea of passing behavior as a parameter. I could go on all day about this. But this is all over the JDK, but this is something that you should definitely think about how to add to your APIs when you reconsider them for Java 8. You can see we have these examples of reduction of boilerplate code, improving the semantics, reducing conceptual overhead, and just basically making your APIs all around better. All right. Okay, so quick break, Brian. So anything interesting on Twitter?
Well, so we have one question here, Stuart, that's going to be near and dear to your
heart. You got the... Are you on?
I'm on now. Okay. So question here is deprecated stuff going to be removed from the JDK? Or what about badly designed APIs? Can they be redesigned in a compatible or incompatible way?
Okay.
I know this is a topic near and dear to your heart,
Okay.
so I won't step on it.
All right, so pound include my Java 1 presentation on deprecation. But I think what we need to do is once we have all these new idioms in there, they're going to be these old ones, we want to find some way to tell people not to use them anymore. And so maybe deprecating them is too strong. Removing them is probably the wrong thing to do because not everybody's going to be able to upgrade all their code all at once. And in fact, maybe they might not ever. And that's kind of okay if the old stuff is working for them. So, but there needs to be some way to mark those interfaces or APIs or methods or whatever to say, you know, this is kind of an old thing, use this one instead.
Yeah, there's something particularly arrogant about saying, well, this old method sucks and you should remove it. And like, I don't care if you're going to break the code of millions of other people because I think this API is ugly. And so, you know, people commonly ask, well, when are you going to remove all of these things? And the reality is, removing things is like mostly downside. There's a lot of people with working code that we would hurt for no good reason other than satisfying our own sense of aesthetic. And so what we really need is a mechanism for guiding people to migrate from the old thing to the new thing. So we had one more question that looked like a good choice for this one now. What is the advantage of using compute if absent instead of Guava's multimap?
Okay. Well, if you're willing to have a dependency on an external library, I think multimap is a fine thing to do.
Yep.
We have considered using importing something like multimap into the JDK. I think it's a good idea. It's probably a better abstraction for that particular thing. I think two things. One, well, we haven't done that yet, so it's not you know. It's not to say that compute if absent, you know, now that we have compute if absent, we don't need multimap, but that's merely an example of using compute if absent. There are a bunch of other ways to use compute if absent and also compute if present and merge and things like that. So there's a general pattern in the new map interfaces of passing in a lambda and that something gets conditionally executed or executed at the right time or something like that. But there's a whole other discussion we should have at some point, but not here, about what enhancements we might want to do to collection. And I think multimap is a possibility, but that's a futures thing.
Yeah, and we did actually discuss that one with the Guava guys, and their recommendation was, yeah, don't take multimap.
Oh, really?
And the reason is, the multimap, if you look at it, it's actually a very large API, and there's like thousands of lines of code that would have to come in. And you know, it was. I mean, we love Guava. There's lots of great stuff in there. We like to steal ideas from there. We talk to those guys all the time. But this particular one didn't really satisfy the the cost benefit analysis because there was a lot of code for a relatively small amount of incremental value.
Okay.
So compute if absent, was a nice trick because we added a default method, which we can do now, great, which was a few dozen lines of code throughout the JDK, and didn't have to pull in a whole new abstraction and several thousand lines of code. So if you use Guava, great, nothing wrong with that, but this was an easier way to get to a significant fraction of that benefit.
Right.
So, okay.
All right, I'll press on. Okay, so now, different use of Lambda, which is for function composition. All right, so now this is an extended use case here about sorting. And so if you've ever had to sort a collection prior to Java 8, there are a couple methods on the collections utility class, collections.sort, and collections.sort with a comparator. Now, there are a lot of use cases for different kinds of sorting, such as I might want to sort things in reverse. Or I just closed out a bug on this the other day. Somebody complained that his collection had nulls in it, and he got a null pointer exception. Okay. Yeah, so what you need to do, and actually, I have a better. The old answer was write your own comparator that has null, or that deals with null. And there's a better answer, which I'll get to in a moment. But this is something that people want to do, which is to have special handling for null. A very common case is you might have a list of some kind of records, and you don't want maybe the records don't have a natural sort order, but something inside the record, like a person's name, that's a string, so that might have a natural sort order. So you might want to sort a list of things by some field or by some, by calling some getter for each of those objects. And so maybe if sort had some kind of key extractor function that could be used to generate the sort key, that would be useful. And then there's another thing too, which is a multi-level sort. So if you have a person with a first name and a last name, you might want to sort by first level sort being last name, and then with people in the same last name, sort by first name. But anyway, to do any of these things prior to Java 8, you basically have to write your own collector. You have to write your own comparator. All right. Okay, another show of hands here. How many people have written comparators? Okay, bunch. Oh, wow. More people than iterators. Okay, how many of you enjoyed that experience? Very few people, right? And so this is what you have to do, right? Given a list of student, sort by age, subsort by a possibly null last name and a possibly null first name. And so I stole the slide from my colleague Mike Dwigo, who had a Java 1 talk here. And basically, this does not fit on the slide, and you could make it small enough to fit on the slide. But you basically have to check all these cases, and return one. Do this one. Right. So halfway down, he says, "Kill me now." So writing your own comparator to do this kind of stuff is pretty difficult, and it's very, very easy to get wrong. So if you write a complicated comparator like this, well, you better have a nice set of unit tests to back it up, because somebody's going to come in and say, "Oh, actually, I also want you to add this other one." Kill me now, right? So let's see what we can do to improve this APIs now that we have this nice Lambda thing here. All right. So I spent the whole last section talking about passing in Lambda as a bit of behavior. So let's try that. Let's consider, this is hypothetical, but this is sort of the design process that we went through. Let's add a key extractor method to sort. So sort by a person's name. That's pretty good. So what that does is, for each object in the collection, it doesn't compare the objects themselves. It runs, for every pair, it runs the key extractor on each one, and that results in some value that should be comparable, and then it compares those. And so that's how the sort order is established. Okay, so this is great for values that are objects, but sometimes you want to sort by values that are primitives, so we need to have variations. The common theme in Java 8 is we did a bunch of primitive specializations, but for only 3 of the most useful primitives, int, long, and double. And so, let's follow that and say, so we add sort by int, sort by long, sort by double. And so we've added 4 new methods. And so, this is not too bad, but this is pretty useful. Reversed. We could add sort by reversed variations in all the primitives, so we need 4 more of those. So now we're up to 8 new methods. And now we want to specialize by nulls, so we could, nulls first, nulls last, but then the primitive specializations of those. So that triples the number of methods, and so now we're looking at 24 new methods. All right, now let's think about a variation that does 2-level sorting, or even an n-level sorting. Hey, it would be cool to pass varargs list of key extractors. Yeah, that way we can do n-level sorting. But we need to, if you want to mix primitives and objects, then you have to provide the overloads for that. So we have to have object and object, object and int, object and long, and I've lost count at this point. I don't know how many variations we have at this point. And in fact, doing a varargs API around this is incredibly difficult. You start to get into a fight with the type system. This is just collections.sort. Now we're going to add, 72. I'll just make that up. I think there's 72 new sort methods. And you have to add them to arrays.sort. And then streams.sort too, that's right. And then, there's the sorted map family, right? And we want to be able to specify all those variations of sorting. Kill me now. All right. So nobody's going to implement all of these and write all the tests for all of these variations of sorting on collections, on streams, on arrays, and on ordered maps. So you can tell that this is going in the wrong direction, right? So we have all these variations of sorting, and so saying, let's add another method that covers this variation, we get a combinatorial explosion of different sorting methods. And so at some point, you start to think about this explosion of methods and how to deal with them. And then you think, this is not the abstraction you're looking for. So at that point, you should say, OK, there's something wrong here. Let's step back from this and figure out a better way to approach it. So the way to do that is the way we ended up with that is, we looked around for a while and noticed, well, gee, all of those sorting things, right? So collections.sort, arrays, streams, and the sorted map stuff, all of those can use a comparator. So let's look at that. So a comparator is a function. And so given two values, it returns an int that tells the ordering of that. And so the key here is to start thinking of a comparator as a function, not some object that has some state or anything like that. Think of it as a function. OK, now if we want to do a reversed sort, then, well, what's the reverse of some comparison? Well, if you look at the comparator API, -1, 0, and 1, how do you reverse that? Just negate it. OK, now if you have a negation, that's a function, and you have a comparator, and that's a function, composing them is actually pretty easy. Just write a little function that says, call the original one, negate it, and return that value instead. Oh, that's kind of nice. How about null treatment? OK, you can write a little bit of logic that ticks off the null value cases, but if the things are non-null, then just calls the original function. That's only a few lines of code. So that's pretty good. So given any comparator, it's pretty easy to wrap some null handling stuff around it and create a new comparator. Now suppose we want to do multi-level sorting. That's actually pretty easy too. So call the first level comparator. If that determines an order, if that returns something non-zero, you got your answer, return it. If it returns 0, only then just call the second comparator. So that's a few lines of if-then-else code. Not too bad. But you can do that with any pair of comparators. Or you can do this with any n comparators, compose them this way. So it turns out that provide your own comparator was sort of right all along. It's just that writing out a comparator was really, really hard. So instead, provide your own comparator, but also have a library that lets programmers create new comparators much more easily. And once you've done this, you have a comparator that can be applied to all of these cases: collections, arrays, streams, and sorted maps. So what we've done in Java 8 is use this to create a whole family of what we call comparator combinators, which are ways of constructing comparators and also combining comparators. So given any comparator, we can create the reverse comparator. Given any comparator, we can layer on nulls first or nulls last over it. Given any two comparators, we can say, call this comparator, then comparing the other one. So we compose those into a single comparator. So if we turn to my colleague Mike Dwigo's example from Java 1 that I showed earlier on, this is what the code looks like now. So we want to compare the ages and then compare nulls last name, and then compare null's last variation on the first name. It's pretty simple. You can read what's going on here. We're first comparing by age, then last name by first name with proper null handling. Pretty easy. We had dozens and dozens of lines of code compressed down to 3 lines here. All right, so what's the lesson here? Well, let's take a page out of the functional programming book. They have this idea of higher order functions, which are functions that consume or return other functions. And that's what we did here. This is very new to Java, but this is actually a fairly old concept. So it's incredibly useful, and it's something we never thought about doing in Java until we had lambdas. The other lesson is, if you start running into a combinational explosion or some other problem that's causing something, look around and look around at existing things and apply new techniques to them. So we really hit upon a good solution with comparators here because it lent itself very nicely to function composition. And then if you have code that uses some of these behavioral design patterns, you might have multiple. Suppose you have some system that uses multiple strategies. Well, gee, you can think about if you had a bunch of really complicated strategies, maybe you could break those down into simpler strategies and figure out ways to combine them in a convenient way. And once you have lambdas, this becomes really easy. Anything useful, Brian? Okay, yeah, I think we should press on. I have a lot of material here. Okay. Okay, a few words about default methods. The main reason we added default methods was to allow for API evolution of existing interfaces. And so most of you probably know that once you've defined an interface, you can't add any methods to an interface without modifying all the implementations of that interface. Otherwise, you're liable to get errors at runtime. And so there's a crying need to figure out how to evolve interfaces in the JDK. And so that's what we did there. We created the default methods interface in order to do that. But there are several ways it's used. Certainly, we added some default methods to the collection interface in that family in order to provide a better interface to streams. But we also use them in the comparator combinators that I just discussed. And then there's another example here where we used default methods to make it easier for people implementing that interface. So if you go back to the iterator interface, most iteration is not intended to have side effects. But there's this remove method on iterator. Actually, I'll show that on the next slide. There's a remove method on iterator, and we've now added a default, which is throw new unsupported operation exception. So if you ever have to implement an iterator in the future, this gets a little easier because you don't have to go in and type this thing in over and over and over again. So what's the impact on the API? Actually, it's sort of a subtle thing here, which is if you're introducing an interface into an API, prior to Java 8, there was enormous pressure to make sure that interface was exactly right. Because if you had it wrong, it was very, very difficult to change once that interface got out in the field. And then you had to deal with evolution of it, like creating interface 2, interface 3, and all kinds of weird things like that. I know various systems have done that, and that's a very painful way to deal with that. So it makes it easier to make design decisions about interfaces by saying, we're not sure about this one, and if we're not sure, maybe we can leave it out, and maybe we can add it later using a default method. And so that's another design trick for designing interfaces. One other quick comment here about default methods is that for the first time, implementation code can reside in interfaces in Java. And so when people say that, they think, oh, wow, we don't need abstract classes anymore. And that's not really true. It's certainly useful in many cases to share implementations that way, but you have to be careful because an abstract class really provides a lot of service for subclassers using protected interfaces, and it can maintain private state and so forth. So that's not present in interfaces. Everything is public in an interface. And so if you try to replace an abstract class with an interface with default methods, what can possibly happen is that things that are intended for subclass use only tend to leak into your client API, and that's kind of a weird API design spell. So I'd be very careful before rewriting abstract classes into interfaces with default methods. So one of the things about interfaces separate from default methods is we've also added static methods on interfaces. And so this is really useful. There's an old pattern of if you have some interface and you want some factories for your utility methods, those have to go into a class. So there's the collection interface and the collections class that has a bunch of utilities on it. That's still useful, but sometimes if you just want to have a couple factories for an interface, you can put those right there in the interface as static methods. But I wouldn't pile everything into an interface. So if you look at the collector interface in Java 8, it has a few static methods on it, which are basically the fundamental static factories for that. But there's also a collectors class that has a bunch of very useful implementations, but they're kind of specialized. So in this case, it makes sense to have certain static methods directly on the interface, but other static methods being in the old utility class pattern. All right, using streams in APIs. So now I'm going to turn away a little bit from language design, or language features, and talk about the new APIs we've introduced in Java 8 and how they can also influence API designs. So in many cases, you might have a class that represents multiple values or an aggregation of values or something like that. And you might want to have an API that lets a client get those values. So the question is, what do you return? And so a common thing to do is to return a collection of some sort, or maybe a list or set or something like that. But in general, a collection of some sort. And there are a bunch of things you have to think about. If you have that collection already in your class, you usually don't just want to return a reference to it, because that lets the client muck around with your internals. So you have to make a defensive copy. Or if you expect the client only to iterate over it, maybe wrap it in an unmodifiable collection and then return that instead. Now there's another thing, which is maybe conceptually your class represents multiple values, but they're lazily generated. So if you need to return a collection, you can either say, okay, well, I'm going to go through and generate all those values, put them into a collection, and then return that to the client. But maybe that's potentially very expensive. So sometimes what people try to do is they try to make lazy collections. And in general, this is really hard. Because a common thing might be, well, suppose the client calls size. Well, if your collection's lazy, do you reify all the elements at that point? That hasn't really bought you that much. So there are a bunch of issues with this notion of returning a collection. That's something that I'm sure many people have had to wrestle with. So in Java 8, consider returning a stream. And so the stream is much more powerful and flexible than a collection. But if you really want a collection, or I should say if the client wants a collection, it's very easy to turn a stream into a collection. But the great thing about a stream is that it's lazy by default. So if you return a stream, there's no requirement to create that whole collection up front. And this is especially useful if the client is just going to, for instance, do a search of the elements and just pick out one of them and then throw the collection away. So the other thing is that what the client might do is immediately start to iterate over the collection and do something with it. But if you return a stream, then the client has all this access to nice filter, map, flat map, all those nice stream methods that it can just apply immediately. So really, there's one case where you really do need to return something like a collection, and that is if repeated read consistency is necessary. So if the client needs to go over the values multiple times, and it needs to make sure they stay the same every time. And so that might change if it gets multiple streams. So let me show you a little example of how returning a stream instead of a collection can change your code and change your APIs. So I have a little example here, kind of written in conventional pre-Java 8 code, where you have something that gets all the items and then returns a collection of the ones that matched a set of tags that have been passed in by the client. So we get a collection of all the items, run through them all, and then accumulate into a result list things that we want, and then we return that. And so at the bottom, you can see how that's called get the tags that match, tag 1, 2, and 3. And that returns a collection. So that's pretty straightforward. But let's look at this get all items method. So as I've defined it in this example, it returns a collection of item. Well, what if it returned a stream instead? Well, if it returned a stream, then all of this iteration in the bottom half of the slide can just go away, and the client can do it itself. So we can call get all items directly and then just filter them and collect them into a list. And then it gets its collection. But it might actually not need to collect them into a list at all, right? Maybe it wants to find one, maybe it's just looking for one thing that matches a tag. So instead of building up them all into a collection that it then iterates over, maybe it just calls find first, it calls filter and find first directly on that stream and gets the one result that it wants. So if you're returning a stream, maybe a whole layer in your API might just disappear because it's been subsumed by the stream's APIs. All right, so now optional has sneaked in here, so I'm going to spend a few words talking about that. So an optional is a wrapper value that either has a value present or that's empty. And the point of this is, just like on the previous one, if you have a method that in many cases, in normal cases, may return no result. And so the typical pattern for this is if you have a method whose description is returns the first such and so, or else null. And so that's a very common thing. And the problem with null, as Tony Hoare called it, the billion-dollar mistake, is that nulls can leak into your programs, and then you get, or you can leak into your data structures, and you can get null pointer exceptions at unexpected times later in your program. So optional is intended to alleviate that by providing a stronger type-safe mechanism for representing either this is a value or there is no value here. It's much more stronger and type-safe than using null. So the typical case is something like a find or a search, or there are also things if you want to find the maximum of some collection or something like that, then there's this extra special there's a special case that it's very easy to forget is suppose the collection is empty. What is the maximum value in some empty collection, right? Well, so if you look at the streams code, max is defined to return an optional for exactly that reason. So here's an example of that. So we have a stream. We filter it and find anybody named Smith. And so now we get an optional out of that. We can say, get the value out of it, but if it's empty, instead print out nobody named Smith. And then an example of using max is, we get all the persons, and suppose we want to have an assertion that there are a non-zero number of persons there, and we want to get the maximum age. So in this case, when we extract the value, we might want to say, if the optional returned is empty, then throw an exception saying, hey, I got an empty person list. Something's wrong here. All right. I'm going to talk about generics for a minute, everybody's favorite subject. Generics are not new in Java 8. In fact, we've made very few changes to generics. A couple changes, but they're pretty obscure in Java 8. But the compiler uses a lot of type inference in dealing with lambdas, and type inference really strongly relies on generics. And so I'm going to switch over to NetBeans here real quick. See what we can. Okay, so I need to mirror this. I'm going to run through one quick example here. Suppose we have. Yeah. Okay. Suppose we have a function that runs through a list of character sequences and does some filtering and mapping and stuff on them. And you can see all the red squiggles here. This isn't working. And why is this? Well, in order for this lambda to be compiled, the compiler needs to know the types of things. And since we're using a raw type for list, it doesn't know what that is. And I don't know how much raw type use there is in the field, but I see Stack Overflow questions for raw type. So I think there's a lot of raw type usage out there, and it's time for everybody to get off of using raw types, because it's almost impossible to make this code work unless you use generics. So when I paste in the right declaration here, all those errors go away. So what happened is, now that we know this is a list of character sequences, the stream contains character sequences, and the compiler's type inference says, oh, okay, since we have character sequences, this CS is a character sequence, and all those types run through the entire rest of the expression, and it works perfectly. But if you don't use generics, that just doesn't work. All right, I have some more demos. I think I'll have to skip them at this point. But the upshot is up your generics game, because the Java 8 APIs and the Java 8 language features really lean very, very heavily on generics. And if you're not using generics, then things are not going to work out well for you. All right, quick summary here, and I think I'm going to run up right to the end here. And just to run through, I think the key point here is Lambda is a huge feature. It enables you to pass in bits of behavior, and that does lots and lots of nice things for your APIs. You can replace a lot of old design patterns by passing in behavior. You can make things a lot more convenient Once you have lambdas, you can use them to combine functions and use higher order functions. It's a different way of programming, and your APIs should reflect that. New features in interfaces, including default methods and static methods, are very useful. You should really consider using streams as a replacement for collections. And you pass those around between different pieces of your program. The streams API is very powerful and it has lots of advantages, including laziness, parallelism, and just built-in traversal, like filtering and mapping. And so that can be very powerful. I talked about optional a little bit and generics. At the beginning, I said one weird trick to improve your APIs. That weird trick is generics. It's an old trick, but it's a really good one, and so I really recommend that you up your level and learn generics. It's about time that everybody does that. And so, unfortunately, I am exactly out of time. Otherwise, I'd take more questions. So thanks for your interest and attention. And thanks, Brian, too, for contributing with this.
So there were a lot of questions on Twitter that were going to be too long to answer. A lot of them were rationale questions. Why did you? Why didn't you? We have a whole panel at 2 o'clock where
in this room.
In this room, which is nothing but answering questions.
Okay.
So bring those questions back at 2 o'clock.
All right, great. Thank you.